Good morning, everyone. Am I audible? Hello?
Yes, ma'am, you are audible.
Okay. So yesterday I explained counter, but I didn't explain how this counter is working. Okay. So this is a digital counter. Okay. This is a 7-segment display. So actually it is converting from binary to this 7-segment. So we can understand how it is working. So this comes under the 7-segment display, which we will study later in uh, this course. Okay, that is 7-segment display, how we are converting this binary number to 7-segment display. So I told you, if the number of bit is 2 and the combinations will be 2 to the power n. So if 1 is the bit, then we will have 2 combinations. So we will call it as modulo 2. Okay, if 2 number of bit is there, then 4 combinations will be there, so we will call it modulo 4. And if 3 bits are there, then 8 combinations will be there, so we will call it as modulo 8 counter. Okay. So we have two types of counter. One is asynchronous and one is synchronous. So synchronous, if you hear the name, you will know it as sync. Okay. So synchronous counter means the clock is same for this. Okay. So the clock is same for this, but asynchronous, it means that all flip flops have different clocks, and clock is not working simultaneously. Whereas for this, the clocks are working simultaneously. So here we are giving this one clock, and the output from this first flip flop, it is going to the input of this second flip flop. So here this is the clock, and the output from the second flip flop is going to the third flip flop. So this is asynchronous counter and how it is working. So here we are using this asynchronous counter because it is easier to count with this asynchronous counter. I will tell you how. So there are two types of counter. One is up counter and one is down counter. So up counter, it is counting from 0 to n, and for down counter it is counting in reverse, means from n to 0. Okay. So this is our asynchronous counter. So here the first clock, it is clock connected to the flip flop clock input of least significant bit. So here we are having this least significant bit, and here we are having this most significant bit. So if we see this truth table, so this is the least significant bit and this is the most significant bit. Okay. So here the clock we are giving to the least significant bit, and here from here we are getting the least significant bit. So this least significant bit is becoming, this output is becoming the another clock for this second flip flop, and the output from the second flip flop, it is becoming the clock for this third flip flop. Okay. And here we have a bubble, it means it is negative s triggered. Okay, that's why there is a bubble. And here we are getting this least significant bit, here we are getting the middle part, second digit, and here we are getting the third digit, which is the most significant bit. So flip flop output is connected to the clock input. Thus circuit is not totally synchronous, as all the clocks are different, so it is not synchronous and it is asynchronous. So here what we are doing, we are actually delaying the clock with each flip flop. So here we are delaying by 1, here we are delaying by 2, and here we are delaying by 3. So this I will tell you how we are getting doing it delayed. So first we need to understand what is a clock. Okay, this is not in syllabus, but you need to understand this clock. So a clock pulse is continuously changing signal that oscillates between high state and low state. So this is like a digital signal which has 1 and 0. These clocks can be different, But here we are using this type of clock 0101, which is constantly changing. So it is a clock signal is a square type. So you can see it is a square type, and it has a 50% duty cycle. So what is 50% duty cycle? It is saying that half part it is 1, and for half part it is 0. So 50 it means half part. So half part it is 1, and half part it is 0. Okay. So two types of triggering is there. One is positive edge triggering and one is negative edge triggering. Okay. So positive edge triggering, when the output responds to the change of in the input only at the positive edge of the clock. Okay, that means when we are getting a logic 1. So this is the uh, rising edge and this is the falling edge. Okay, so whenever there is a rising edge, that becomes the positive edge triggering. It means like when it is going from 0 to 1, then it is changing. Means whenever the clock is becoming 1, then the our circuit is working. So that is positive edge triggering. And here negative edge triggering means it is uh, falls in the falling edge of the signal. So whenever we are going from 1 to 0, then our circuit will work. So this is our negative edge triggering. Okay, so whenever there is a logic 0, only then our circuit will work. So this is our negative edge triggering. Any doubt in positive and negative edge triggering? Salil, your video is on. So any doubt in this positive and negative edge triggering? Any doubt?
No
No,
doubt, ma'am.
ma'am.
Okay, so this is a 3-bit ripple counter. So if we have 1 bit, then what we will do, we will only use one flip flop. Okay, so this counter we can either make it from JK flip flop, we can even make with D flip flop, and there is a T flip flop also that is not in syllabus. With that also we can use. Okay, but here we are using this JK flip flop. So for 1 bit, we will have only one JK flip flop. For 2 bits, we will have two flip flops, and for three, we will have three flip flops. Okay. So here in JK flip flop, yesterday we studied. So here in, I will just do a quick revision for JK flip flop. Okay. So in JK flip flop, we had two inputs J and K. We had a preset and clear to enable the circuit. Means this preset and clear is working as a switch. Q and Q dash is the output, and we have a clock. Okay. So first we have to see the preset and clear. So here it is working same as our SR NOR gate. So uh, if we do 0 1, our q is becoming 0 and q bar is becoming 1. If our give 1 0, then our q is becoming 1 and q bar is becoming 0. And if we give 1 1, then this is actually enabling the circuit. So here, because we have this as negative edge triggering, so here 1 1 will work. But here if we see the circuit in logistim, this is a positive edge triggering. So here it will work reverse. So here our 0 0 will work. Okay, so this is how we are starting this circuit. If so for here, and we have to enable as 1. So for here in negative JK flip flop, 1 1 is the enable circuit. So if here for positive edge triggering, it will be 0 0. Okay, so if I show you, if I'm changing this, you can see it is changing. But if I change this preset and clear to any other value, you can see it is not working, because this is an enable key. We have to first switch on this JK flip flop this with a 1 1 condition, but because this is positive S triggering, we have a 0 0 condition. Okay, we have to put it to 0 0, only then our circuit will work. So this is how we will start the JK flip flop with preset and clear. Then we will start using this JK. Okay, so First condition is 0, 1.
Ma'am, just
Hmm.
1 second.
Hmm.
So basically, you're saying that if you switch out both preset and clear, it's what exactly is it?
This is
Like,
working like a switch. Okay, so the condition is 1, 1 for this negative S trigger. Okay, that condition is 1, 1. But because we are having this here in this circuit, we are having this positive S trigger. So here we have to put it 0, 0. This you understood, na?
yeah, that I understood.
Okay, so we have to put 1, 1 for this negative S triggering, but here we have to put it as 0, 0. Okay, so
Okay.
you can see that if you put 0, 0, this this circuit is working, this flip flop is working. Okay, but
Hmm.
if you put it to any other case like 0, 1, you can see it is not working.
Okay.
1, 0, it won't work.
Okay.
Okay, and 1, 1 also, if you put, it is not working. It means 0, 0, it is acting like a switch for this
Okay. Okay.
positive S trigger, and for negative S trigger, it is 1, 1. So you have to write it as
Okay.
1, 1. Okay, only
Okay,
then
ma'am.
our JK this will work.
Okay.
So JK is working same as this flip flop, but if we here SR latch, but here we have a clock. When if we don't change the clock, this won't change. Okay, so this is a we are every time we are saying until and unless we change the clock, this won't change. So 0, 0 is whatever the value of q and q bar was. So this is a memory state. So it will remain constant for 0, 0. You can here see here 0, 0, whatever the output was there, it will be same. So if we uh, so we will first say this condition 0, 1. So if we put 0, 1, so see it is not changing until and unless you change the clock, it is not changing. So actual value should be q should be 0 and q bar should be 1. So this is the final value. If you, even if you change the clock, this is not changing. So as our q is 0 and q is the main output, we will say q is reset. For 1, 0, if we do 1, 0, if we do 1, 0, then it is not changing. Okay, then we will change the clock. So as it is positive S triggered, it means it will work when we are giving a 1. So it is changing Q to 1 and Q bar to 0. Again we are changing, it is not changing. So this is the final output for this JK flip flop. So Q we are getting as 1 and Q bar as 0. So that's why we are saying the Q is set, because Q is the main output. So 0, 0 is the memory state. So if you go back to 0, 0, we can see that whatever the output was there, we have the same output. If we do 1, 0, so the if we do 0, 1, then output is 0 and q is 1, q dash is 1. So if we go back to 0, 0, this output is not changing. So that is a memory state. Okay. But for this last condition, JK, for this last condition, okay, this is like one more drawback of this D flip flop was that we are not able to use this 1, 1 condition. So we have removed this in JK flip flop. For 1, 1, we can see it is giving a Q bar. Okay. So whatever the original output of Q was there, we will just get reverse of that. So here you can see Q is 0 and Q bar is 1. So we will put a clock. For 0, it is not working because it is positive as triggered. Again, when we give 1, it is okay, sorry, for JK1, 1. So Q is 0 and Q bar is 1. So with 0, it is not changing. But if we give it as 1, you can see it is just reversing. And again, we will keep this JK as 1, 1. And again, if we give a clock, you can see that this is changing. It is Q is 0, then again we will give a 1 clock, then it is coming as 1. Again we will give another clock, then it is going to 0. Okay, so actually this you understood now. 1, 1, it is just becoming opposite, it is toggling. Yes. This you understood, now?
Yes, ma'am.
Okay, so for 1 1, it is, you can see it is toggling with each pulse. So actually we are using this condition to make our counter. Whenever we are giving a clock pulse, it is changing. So we will use this condition of JK flip flop to make a counter. Okay, you can see with each clock it is changing. So that's why we have used this JK flip flop, because with each negative, this is negative S triggered. So with each negative pulse, it will change. Okay. So for 3-bit ripple counter, we have 3 flip flops, and n is the value. The n bits are there, so the counter can count up to 2 to the power 3, means 8. So it can count from 000 to up to 111. Okay, this you understood yesterday. So here the output of this first flip flop, it is working as the input of the second flip flop, and from here we are getting this least significant bit. This part here we are getting this least significant bit. From here we are getting this middle term, and from here we are getting the most significant bit. It means this part, most significant bit, we are getting this part. Okay, so here what they have done, we have kept j and k as 1, so that it will keep on toggling for that part. So that's why we have put jk as 1. Okay, so here all the JK inputs must be taken to logic 1 to enable the binary counting. So because when JK is 1, then it is just becoming reverse with every clock. So that's why we are using this JK flip-flop. So clock connected to the flip-flop clock input on the LSB bit of the flip-flop. So the clock is connected to this least significant bit. And one more thing, you can write the output of this first flip flop is going back to the input of the second flip flop. And output of the second flip flop is going to the input of this first flip flop. So the clock for this second flip flop, it is the output from this first flip flop. And the clock for this third flip flop, it is the output from the second flip flop. Okay. This I explained to you that it is changing from 0 to 1, 0 to 1, 0 to 1, and 0 to 1. Like this, it is changing. And second part is like changing after two parts, 0, 0, then we are getting 1, 1, then we are getting 0, 0, then we are getting 1, 1. And in third, we are getting like 4 zeros and 4 ones. So how we will count like that? So this 3-bit counter is a negative S triggered. So in at first we are giving a 0, 0, 0. Okay. So everything is 0, 0, 0. So we can say JK flip flop, it is working as here it we have used negative S triggering. So whenever we are getting a 0 or this falling edge, it will change, because in JK for 1 1 it is changing to opposite. Okay. So first we are giving a 0. So here with the clock, here we are getting first negative. So here it was changing from 0 to 1. Okay. Then again here 1 is coming, so it is not changing. So it is negative S trigger. So here the second negative S trigger is coming. That's why it's changing from 1 to 0. Then this third negative S triggering is coming. That's why it is changing from 0 to 1. And this negative S triggering is coming. It is changing from 1 to 0. So like this, we are getting this table. Okay. Then how we will get this table? That's why they have said clock connected to the flip flop clock input. Output change is delayed more for each bit towards the MSB. Okay. So this is delaying the clock by 1, and this is delaying the clock by 2, and this is delaying the clock by 4. Okay. So here you can see the output of this first flip flop. It is becoming the clock of this second flip flop. So this clock is not for this output. Actually, this is becoming the clock for the second output. So initially we are getting a 0. So whenever we are getting a negative S trigger, then it is switching back to 1. And whenever we are getting the next negative S trigger, then it is switching back to 0. Okay. So this is why it is getting delayed by 2. And for this third JK flip flop, this is working as a clock. You can see this is working as a clock. This output is working as a clock for this third flip flop. Okay, so this is work as a clock. So this is how we are getting a delay of 4. So initially we will give a 0 and we are not getting any negative edge triggering. So here we are getting the first negative edge triggering. That's why it is going from 0 to 1. Okay. Then again it will go to, uh, you can see here again we are not getting any 0. So that's why it is 1. And again when we are getting a 0, only then it is changing back to 0. So understood how this is working? JK flip flop is working. Any doubt?
Ma'am, can you repeat again?
What you are not understanding in this? Which part you are not understanding?
Ma'am, left side clock.
JK flip flop you understood now. This 1 1 we are using this part 1 1 this part. This you understood because it is
Yes,
making
ma'am.
it opposite. Okay. So this you understood. Okay. Then half thing you have understood. So what we can say in this least significant bit, it is changing from 0 to 1, 0 to 1. So every 1 bit it is changing 0 to 1. This you understood?
Yes, ma'am. This part is on.
And this is changing after 2 zeros and 2 ones. This you understood?
Yes, ma'am.
And this is changing after 4 zeros and this is changing after 4 ones. This you understood?
Yeah, ma'am.
Yes. So here in this flip flop, what it is doing, it is delaying our clock. Okay. So here we saw in JK flip flop. So whenever JK is 1 1 and we are changing this, okay. So with positive edge triggering, if we give a 1, this is totally changing. It is flipping. Okay. So we are using this part. So whenever there is a positive edge, whenever we are giving a 1, it is changing. So that's why we are using this JK flip flop. So here you can see this for this first JK flip flop. Okay, our clock is there. First clock is there. So initially we are giving this clock. We are getting a 0 and a 1 and 0 and a 1. Okay. So this is negative S triggering. So whenever we are getting a 0, it is changing. This you understood? Negative S
Yes,
triggering.
ma'am.
So here we are giving a clock. Okay. So first this is negative S triggered. So whenever we will get a 0 now only that time or in the falling edge it will change. So initially we are giving everything 0. Q0, Q1, Q2, everything as 0. Okay. So for this part Q0, we can say this is the clock. Okay. So whenever this is falling, so we saw na in JK11 condition, whenever there is a positive, like when we change the clock to 1, it is just changing, becoming opposite. So here, because it is negative as triggering, whenever we are giving a 0, it will just become opposite. So that's why it is going from 0 to 1. Okay. This you understood?
Yes, ma'am.
Mm. So where is the second? Here again we got a 1. Okay, so that's why it is not changing here. Then again here we saw this is the second negative S triggering. So it will just become reverse. So it is changing from 1 to 0. Okay. Then again for here it is negative S triggering. So it is changing from 0 to 1. So this part you understood now? How it is changing?
Yes, ma'am.
That's why it is changing from 0 to 1, 0 to 1, like that it is changing. Okay, so this part is how it is working. This you understood now?
Yes, ma'am.
So for this Q1, okay, how this Q1 is working. So you can see now in this Q1 there is two zeros and one ones. So if we use this clock, then it will the counting will become same. So what we are doing for the clock for the second, we are taking the this output. This one we are taking as a clock for this second flip flop. Okay. So this is the clock for the second flip flop. This part is the clock. Okay. So initially we gave a 0. So where is the first negative edge? Where first negative edge is here. Okay. That's why here from 0 it will change to 1, and there is a delay of 2. Here we are getting two zeros. Understood this part? This is the clock for the second part. Hello?
Yes, ma'am.
Okay, so where is the second clock, second negative edge triggering here? So it is here. So that's why it is 1. So here we got two ones. Okay, two ones here. And we saw that negative edge triggering is here. That's why it became 0 here. And for third part, you can see this output is the clock for this third flip flop. Okay, so this is the clock for this third flip flop. So it is negative as triggered. Now that's why for initially we will give a 0. So it is negative as triggered. Even if we give a 1, it won't change. So for next negative edge, this negative edge will be there. Only then it is changing to 1. So that's why we are getting a 4 zeros and 4 ones. So after 4 ones, we can see here we are getting from 1 to 0. So that's why it will change here. Understood this timing diagram?
Yes, ma'am.
Okay. Same thing will happen with 4 stage binary counter. So negative S triggered. So here bubble is there. It means negative S triggered. This is least significant bit. And here we will get the most significant bit. We will give a input in the least significant bit. We will keep both J and K as 1, so that it will get inverted output, inverted Q over here. And here we will get the first Q0, Q1, Q2, Q3. Okay. So this you have to explain, and we will explain that for least significant bit we will give one clock, and for the second flip flop we will give the clock as the output from the first flip flop, and for second we will give the clock from the second flip flop, from the output of second flip flop, and for the fourth flip flop we will give the uh, input for the clock from the third flip flop, output of the third flip flop. Okay, this is explained over here, so you can explain it there in your exam. But in your exam, this 3-bit up ripple counter is coming. So just remember the circuit. You have to make a JK. From here, QA is coming, from QB is coming, and this is going to the in the clock of the second flip flop, because this is causing a delay. This will cause a delay by this will cause a delay by 1 in the clock. This will cause a delay by 2 in the clock, and this will cause a delay of 3 in the clock. Okay. Sorry, delay of 4 in the clock. And JK is put as 1. Just this you have to make the circuit. So for 4 we will have 4 JK, and you can write this. Each state successively divides the clock input signal by a factor of 2. So here 1 delay is there, here 2 delays there, here 4 delays there, and here 8 delays there. Note that logic 1 is transferred to the respective Q outputs on the falling edge. So because it is negative as triggered, so we are getting in a falling edge. So JK is put at 1, and clock connected to the flip flop on least significant bit. Output change is delayed more for each bit towards the MSB. So with each flip flop, the output is getting delayed. Okay. So this is the clock. So initially we are giving all 0. So whenever first negative edge triggering is there, so first negative edge triggering there, it will just flip from 0 to 1. Okay. Then again the second negative edge triggering is there, so it will change from 1 to 0. Then this third is there, so it is changing from 0 to 1. For here, For this QB, this is the clock for this QB. In the circuit diagram, you can see this Q0 it is written. So that is the clock for this second flip flop. So this is the clock for this second flip flop. This is not the clock for second flip flop. This is the clock. Okay. So initially we will give a 0. We can see this is the first negative edge triggering. So it will flip from 0 to 1. So here is the second negative edge triggering. So it will change from 1 to 0. And this is the third. So it will change from 0 to 1. Okay. And for QC or this Q2, this Q1 is the or QB is the clock for this third flip flop. Okay, so this is the clock for this third flip flop. So initially we will give a 0. So whenever negative edge triggering is there, so we will get from 0 to 1. And here second negative edge triggering is there, so that's why it will go from 1 to 0. Third is there, so it is going from 0 to 1. So here we are getting delay of 1, here we are getting delay of 2, and here we are getting a delay of 3. Sorry, 4. And here we will get a delay of 8. So for fourth part, this is the output. This is the output for this clock. So initially we are giving 0, but here is the negative S trigger first. So it is changing from 0 to 1. And here is the second negative S trigger. So it is changing from 1 to 0. So this is how we are getting this 4-bit binary counter. Okay. Any doubt? So we will see this 8-bit binary counter. So here 0 is for up counting and 1 is for down counting. So here 8-bit numbers are there. Here it is for 8-bit numbers only, and here we are using D-type flip-flop, and this is positive S triggered. Okay, so with every 1 it is changing, but our circuit is opposite. It is negative S triggered. So with a 0 it will change. So if we give this clock, so for 0 it is not working. For if we give one more clock, then you can see we are getting a 1. So this will change every other time. So this first flip flop is working for this. So again we give 0, again we give 1, then it is converting back to 0, and this second flip flop will work and this 1 will come. Then we are getting 1 1, and like this it is changing. So this is an up counter, and if we change this to 1, it will become a down counter. Any doubt in counter? Hello? Any doubt in counter?
No, ma'am.
Okay, thank you. So this was the question. This will not come in exam. I told you this will come in exam. 3-bit triple counter. So study this. So this is in your book. This is the question. This is the input, and this is the output. So how you will construct the output? Okay. This is actually very advanced level question. So I don't think this will this type of more questions will come. But because this is given in your book, this can come in external. This question only, but any other waveform it won't come, because this is like advanced level question. This should not be there for first years. So here what they have done, they have put two JK flip flops. So this will delay for 1 and this will delay for 2. Okay, how our counters are working. So this is also negative S triggered. So this is wrong in the book. This is negative S triggered. So I have drawn extra negative S triggered, and one input we are sending from here to here, and one input we are sending from this side. Okay, direct input we are sending from this side, and then we are and getting this both inputs. So here we can say that what we are getting here, we are getting a delay. So whatever we got a delay from this part. Whenever first negative S triggering is coming, then it is changing from 0 to 1. Then here again it is changing, negative S triggering is there, so it is changing from 1 to 0. So there is a delay of 1. Okay, So to make a delay of 2, we have used the output from this pulse as a clock for this pulse. So there is a delay of 2. So with first negative edge triggering, it is changing from 0 to 1. And for second negative edge triggering, it is changing from 1 to 0. Okay. And for third, it is changing from 0 to 1. So this is the signal. So this is the QB signal is coming here, and we are taking this signal as direct signal. Okay. And here we are using this NAND gate. So we have to AND gate. So here we have to AND gate this signal, and here we have to AND gate this signal. Okay. Here we have to AND gate this signal, and here we have to AND gate this signal. So for AND gate, what is the truth table? For AND gate, what is the truth table? Hello? AND gate, A dot B. What is the truth table for that? Two input AND gate.
Ma'am, 0001.
Hmm. So it is 0001. Okay. I will just open it. So this is AND gate. Okay, for 00 we are getting all. AND gate for 00 we are getting a 0. For 01 also we are getting a 0. For 10 we are getting a 0. And for 11 we are getting a 1, because it is A into B. So same thing we will use it here. So here, see, we are getting a 0, and here there is a 0. That's why we are getting a 0. Again there is 0. Sorry, this and this signal. Okay, so here we are, everything is 0. So that's why a 0 is coming here. Okay. Then again we have a 1 here, but over here we have a 0. So that's why we are getting a 0 over here. But here we can see 1 is from here to here, and whenever here it is a 0. So that's why we are getting a 0 here. So we can see 1 is here, and we have 1 here. So 0 into 1, we are getting a 1. Then 1 into 0, again we will get a 0, and 1 into 1, we are getting a 1 here. Then again we can see everything is 0. So that's why we are getting a 0 here. Then, but here we are having a 1. But in this signal, we are having a 0. So 0 into 1, again we are getting a 0. Okay. And here we are getting all the ones. But here we have a 101. So here 00 will, 0 into 1 will become 0. So that's why this signal is coming. Any doubt in this signal?
No, ma'am.
So actually, this is advanced level question. I don't think so. This type of questions will come. Even if will come, the same question will be coming in the exam, and I think so. They will send the model question paper for you, so you can understand what type of questions it will come. So we will start with shift registers. So I started it yesterday. A shift register is a sequential logic block made up of flip-flops that allow parallel or serial loading and serial or parallel output, as well as shifting bit by bit. So actually it is used for shifting the counters. Here also in this counter, it is not properly shifting, but it is like shifting only. Like if you see the counters like this, you can see it is shifting this 0 to 1 and 1 to 0. So like it is shifting one by one. So this it is changing from 0 to 1, like, so it is like shifting. Okay, and two zeros and two ones are there. So again two zeros and two ones are there. So it is shifting, like with each count it is shifting downwards. Okay, so this is also one type of shift register. Means just I am giving an explanation. This is not a shift register. So I am just telling you in terms of counters how this is shifting. So this, if we take this 0, okay, so it is shifting from here to here and shifting from here to here. So it is shifting like down, down, down. So this is a shift type of register. So here they share a single clock, which causes the data stored in the system to shift from one location to the next location. Okay. So two types of shift register is there. One is the shift left, and one is the shift right. Okay. So if this is our term, so zero, a multi-bit register that moves stores data bits left right one position per clock cycle. Okay. So one clock cycle will be 0 and 1. I will just show you. So this is, if our clock is there, this clock is there, one full cycle will be this 1 and 0 combined. So this full cycle is one clock cycle. Okay. Because either it is positive edge triggering or it is negative edge triggering. So we have to take this full cycle of the clock. So this is also working with the full clock. So if this is our term 0 1 1 1, and if we are shifting towards left, so this will shift by 1. Okay, so this one will shift here, this one will shift here, this one will shift here, and whatever you have put, like if you have given 0, so 0 will come here, or if you have given 1, then it will come here. If 0 is there, it will become 1 1 1 0, and if you have given a 1, so it will become 1 1 1 1. Okay. So this is our left shift, and we usually use our right shift. So if we have a term 0 1 1 1, and so it will shift towards right side with each clock cycle. So this one will go out, and this one will come in this place, this one will come in this place, this 0 will come in this place, and whatever you have given, right shift, I don't know what is I. So if it is you have given 1, so it will become 1 0 1 1, and if you have given 0, then it will become 0 0 1 1. This is clear? Right shift and left shift. Hello? Hello? Anyone? This right shift and left shift, it is clear, na?
It's clear, ma'am.
Thank you. So here also we are using this JK flip flop. Okay, so with each flip flop we are giving a delay, and this is how a 4-stage shift register of JK flip flop is there. Here also I think this is negative edge triggering, but in the book it is wrong. They have not given this negative edge triggering, so that's why I have put a negative edge triggering. Okay, so in the book they have given just this part. So this part is delaying the first clock, this part is delaying the second clock, and you can say that clock it is individual. Okay, clock it is individual, so that's why there is a more delay. So this is how our shift register is working, and this is the clock. Okay, so for first negative edge triggering, it is changing from 0 to 1, so there is a shift. For second part, actually here it will become this part j will become actually 0. Means the combination will be different, that's why it is getting delayed till here, and the third part it is getting delayed from here, this jk that will become like 0 1. So that's why we are getting a delay till here. Means if you see this table, if you see this table, because j and k are changing, that's why there is a delay. That's why we are getting a delay here, we are getting this delay here, and we are getting a delay here, and this is how we are getting the circuit. So first negative edge triggering, we are getting a 1 here, with second negative edge triggering we are getting a 1 here, and with third negative edge triggering we are getting a 1 here, and with fourth negative edge triggering we are getting a 1 here. It is changing from 0 to 1. So this is given in your book. Okay, this timing diagram and this. but actually this is not in the syllabus, but last time this was also not in the syllabus for last class, but they have given the question this CISO and this PISO in the external. That's why we have included this in the syllabus. Okay. So registers are four types. One first is serial in, serial out. So this is coming in this exam, serial in, serial out. Okay. So serial in, serial out. So then, serial in, parallel out, then parallel in, serial out, and parallel in, parallel out. Okay. In, serial out, the data for inputs will be data, and there will be a clock. So with each clock, like usually we are using this right shift only. So with each clock, it will shift like this, and one part will come out. Okay. So this is serial in, serial out. So this is serial wise. Like if I make a queue of all the people. Okay. So if I make a queue and one each person has to go and book a ticket or something. So like if first person is done, he will go out, then second person will come. So the queue will shift like this, and if some more people are coming, then queue will they will add to this queue. Okay. So like that, serial in, serial out will be there. But if I can say that if four counters are there, okay, and you people are in queue, so data will go in a serial way, like one data will go, but it will come out at the same time. So if four ticket counters are there and data is going in, but if each person goes to each counter, you can uh, get the ticket done at the same time. So that is a parallel out. Okay. And here but one person will go like one time each, and then at the same time it will go out. So if I do the serial in, then it will take like four steps to get in and four steps to get out. But here if serial data in is there and four counters are there, so you have to get in the four times, and you will like get out at once. Like you will need four steps to get in this box, but only in the fifth step you will just go out all at once, or all will book tickets at once. So in parallel data there is a no queue. Each person is standing in one line. Okay. And four counters are there, so each person is getting ticket at the same time. So one step they will take to get in, and one step they will take to get out. So this is parallel in, parallel out. And parallel and serial out means at once they four lines are there, but only one counter is there. Okay. So at once they will get in the box, but it will take like four times to get out of this box. Any doubt in the serial in CISO, PISO, SIPO, PIPO?
No, ma'am.
Okay.
Ma'am, but this is not the IIT one, right?
It is there.
Ma'am, register type, you told not to write the questions.
I have given a new syllabus now. I told after completing this you write the questions, I told you.
You told microcontroller and shift registers are not there.
But I sent a new syllabus because two classes are extended now. Last class there was no class. It is extended to two classes.
But it will take time to learn it, right? Because you already did that questions and now we have to learn that too. And now we have to learn this too. How much will we learn?
See, I'm not taking the last class. Okay, if I like, I can take this last class and can complete this microcontroller. But I will give that class for studying now. I told it last week
Okay,
only.
ma'am.
This shift registers and this is coming.
Last week you told it is not coming, but okay, ma'am, we'll do it.
No. This week I told it is coming. Because I sent the new syllabus by last week only. I don't know when I sent, but I sent it. Because two extra classes were there now. This week we got the notice that two extra classes are there. That's why. I sent it on
18 January, ma'am. You have sent it already.
mhm. And I have even said that this will come counters, like I even told that 7 parts are there, so one asynchronous counter will come and with 7 shift register will come. There are 5 questions, okay. There are 7 questions and 5 you have to answer the 5. So uh, if you are confident on those 5 questions, then you study 5 questions, no need to study counter and shift register, okay.
Yes, ma'am.
Okay, ma'am.
So this is the circuit for shift register. So whatever was happening here, it is working like same. So with each cycle, we are getting a delay. Okay, so this is the first counter. So here what we are doing, like our number is 01111 and we are introducing 00. So here we are cleaning the data. So whenever we are sending a 00, this 1 is coming out. So this is a shift register. It is shifting the data from here to here. So that's why we are getting this as first output, this as second output, and this as third output. So this is Q0, Q1. Actually, hmm. Sorry, this is the first term, this is the second term, this is the third term, and this is the fourth term, and this is the fifth term. Okay, so initially our value was 0000. Then we introduced a 1. So we are introducing a 1. So this 00 will shift here, and this 0 will completely go out. Okay, then we are introducing another 1. So this 0 will go out, and this 1 will come in. And like this, if we introduce one more 1, so 3 ones will be there, 1 0 will be there, and this will go out. And if 4 ones are there, means one more 1 is there, then this 0 will also go out, and here we will get a 1. So here we are getting a serial in and a serial out. Like one by one, serially it is coming in, and one by one it is going out. So this is the timing diagram. Yesterday I explained this, how we are entering the data and how we are exiting the data. Okay. So original, this is our data 0000. So if we introduce a 1, so this 1 will come here and this 0 will go out. Okay. And if we introduce a 0 here, this 1 will shift here, this 0 will shift here, this 0 will shift here, and this 0 will completely go out. And we can get a 0 here. If we get a 1 here, this 1 will go in, this 0 will come here, this 1 will go here, and this 0 will come here, and this 0 will completely go out. So this is how we are entering the data. But if we have to clear the data, we will introduce 0000. So 4 times if we introduce 0, our this full 4-bit number, it will become 0. So this is the operation for serial in, serial out shift register. So in last external PISO, they have given a PISO. We don't know whether it will come in exam or not. So it is parallel in, serial out. So this is not coming in internals. So this is the circuit. So I told you here, parallel in means everyone will go into the box at one time, but by one it will go out. So it will go at once. For in, we will only need one step, but for going out, we will need 4 steps. So this is parallel in, serial out. So this is a circuit diagram. So our number is this one. Uh, so our number is this part 0000. So it will go at once, but it will come through shift part. So it is shifting here, and it is going out. Whereas in serial in, you can see that you needed 4 steps to enter a number and 4 steps to take out a number. Okay, but here we need only 1 step to enter the number, and we need 4 steps to take out a number. So this is parallel in, serial out. I think number is 1111. So initially we are entering the number, and this is how they are exiting. So any doubt in serial in and parallel out, you have to remember this circuit. Okay, this is only coming, just remember the circuit, it is same. But here in CISO we have a common clock. Okay, this is synchronous, but here in this up counter, 3-bit up counter, you can see the clock is one after the other, one after the other. This is asynchronous. Here we have negative S trigger, so same negative S triggering is there. JK is 1, and from here you are getting first bit, here you are getting second bit, here you are getting third bit. So this is 3-bit. For 4-bit, only 3-bit is coming in the exam, so this 3-bit will be there. For 4-bit we have 4-bit, and for this CISO, because only one output is there, so that's why here we are not getting any output, serial in, serial out. So here will be the serial output data. Okay, so this data will shift from here to here. If it was serial in, parallel out, then the data will come out from here, but it is serial in, serial out, so one input will be there and one output will be there. Any doubt? Hello?
No, ma'am.
Okay, you can write your roll numbers and leave. On Saturday, if you want to study, you can study. Okay, just come to the class, write your roll numbers and leave. If anyone has a doubt, then I will discuss it on Saturday, and I will discuss the question paper on Saturday. Okay. And please submit the assignment by today. The questions you are not able to do, just don't do it. But complete it and send it by today.
Okay, ma'am.